Good day, everyone. Today's going to be a little bit of an interesting episode. It's going to start our Quantumania series.
And I think I can safely say that nobody understands quantum mechanics.
Now, before you turn off the video because you heard the wrong word quantum, we'll make this fun. And in other news, my name's Billy.
I'm Robert.
And we will be talking about the double slit experiment. That's what we'll be talking about today.
Double hole.
Yeah. Oops. I'm gonna call that the two-hole experiment. But anyway, before we get into that, I'm gonna ask all the viewers really quick a question.
Okay.
So, everyone out there, and I'm sure Robbie will be able to answer this, but don't answer it right away if you want to answer it. So, how does a parachute work? Take a moment to think about that. Okay, your moment's done. Rob, do you want to answer, or do you just want me to say?
You go ahead. I'm not going to shine off your moment.
Okay, so first of all, the reason why I say this is that I'm sure a bunch of you out there would be able to have a guess about what's happening, even if you haven't gone parachuting or skydiving or anything with a parachute. I'm sure you have an idea of what's happening. I'm sure you have an idea that it's something to do with the big surface area and it's getting caught in all the relatively stationary air molecules, and it's slowing it down. It's slowing you down if you're skydiving or whatever is attached to it. So I'm sure that a bunch of you probably had an idea of what was happening. How did we know what was happening, even if we've never actually looked up what was happening or experienced what was happening? That is because we have built up throughout our lives our intuition on how things happen at our scale. With wind, we've had wind every day. We've seen papers get blown off tables and out of our hands, maybe. We've built up our intuition throughout our lives to be able to guess what would happen in that scenario. And the reason why I'm asking you all this question is that people say quantum mechanics is hard because it's hard to guess what will happen. The reason why it's hard to guess what will happen is because we haven't spent any time of our lives building up an intuition for quantum mechanics. Our intuition about how things work at our scale doesn't work for the really tiny things. We just haven't spent enough time looking at it and building up our intuition. We just build up our knowledge base. And that's what we hope to do here. That's the goal. So, what is going to be the big thing that me and Rob have chosen to talk about in order to build up this quantum intuition from the ground up? What exactly is this monumental thing? And we chose the two-slit experiment, or the double-slit experiment, the two-hole experiment. A lot of names for this thing. We've chosen this one because a famous physicist named Richard Feynman once gave a bunch of lectures at Cornell, and he chose this one to explain quantum mechanics. And in his words, the reason why he chose the two-slit experiment, and if it's good enough for Feynman, it's going to be good enough for us. Take this one experiment, which has been designed to contain all of the mysteries of quantum mechanics, to put you up against the paradoxes and mysteries, and peculiarities of the nuance 100%. Any other situation in quantum mechanics, turns out, can always be explained afterwards. I say, you remember that case of the experiment with the two holes? It's the same thing. So, if it's good enough for him, it's good enough for us. Now, I would actually disagree with Feynman a little bit. I'm splitting hairs here. You can't really get entanglement out of it unless you start, because entanglement is inherently two different things.
Mm-hmm.
Entangled. So you can't really get entanglement unless you start looking at your measurement devices and start adding those into your... So I'm splitting hairs there. But for the most part, anything can be explained. And maybe in another episode, we'll talk about entanglement. And we can pull entanglement out of this thing.
Mm-hmm.
Would you like to add anything?
You're pretty good so far.
Okay, good. Okay, so the whole point of today is to build up this quantum intuition on what's happening. So what we're going to do is we're going to break this experiment up into 3. The first one we're going to be doing is if we perform it with marbles. The second one is when we perform it with water waves. And then the third one is going to be with some electrons. And we will chapter this video so that way you can jump between them if you need to. And we'll also take a little diverge in the middle to talk about waves a little bit, just in case some of us aren't familiar with some of the properties they have. But I'm getting ahead of myself. So the 2-hole experiment. So this is the 2-hole experiment. 2-hole experiment has a source and a back wall, and in between the two is another wall, but with 2 holes in it. In this case, we have a hole A on the left-hand side and a hole B on the right-hand side. And the color coordination will always be A will be light blue, and then B will always be red. It's going to be the same thing throughout the whole video. And the source just changes depending on what we're talking about. And we're going to be looking at this from a top perspective, which is this. So this is going to be the cross-section of the top. The reason is it just makes the analysis a little bit easier. That way nothing obstructs our view of what's actually happening. So, marbles. That's what we're going to start with. Marbles. Oh, yeah. Now, even though this is a thought experiment, I'm on a budget, so our marble launcher here will be unpredictable. It's not going to be that great. It's not going to be very accurate. And what I mean by this is that we can't predict whether the marble is going to go through A or a B. Now, the second thing is all these marbles, even though the marble launcher isn't that great with accuracy, it launches all of them with the same speed. Every single marble will have the same impact on the back wall. And the marbles also come in lumps, I should mention that. So by lumps, I just mean we have one marble, and that's it. It doesn't spread out. It's where it is, localized somewhere. And all the marbles are indestructible as well. So if we look at the back wall, we're going to see a full marble there. It's not going to break up. And we're going to say that the marble launcher takes about a minute to reload. So only one marble will hit the back wall. We can't have 2 at the same time because the marble launcher only shoots 1 at once. There's going to be a delay between each of them. So that's everything we need to know about the setup for this. So the source is unpredictable. We don't know whether you're going to go through A or B. Marbles come in lumps. That's a Feynman term that I stole. And only one marble is going to hit the back wall at a time because the marble launcher is slow. Now, what are we going to be measuring with this? What we're going to be measuring here is the amount of marbles that hit the wall at a given location. So we're going to picture this back wall is made of Play-Doh. And every time it gets hit by a marble, it gets dented a little bit. So if it gets hit with a marble in one spot, it's dented by a certain amount. If it gets hit in the exact same spot by a marble, its indent is twice as large. Then if it gets hit by 3, it's 3 times as large, and so on. So we're going to be measuring how many times the marble hits within a certain location. And just to have some bookkeeping devices, we're going to call NA, the amount of marbles that went through hole A, and then NB, the amount that went through hole B. And say if we don't know whether it went through hole A or B, we'll call it NAB. And it's going to be purple because it's the sum of the red and the blue. So this is everything we need to know. Now, what exactly happens when we run this? So if we run this for a long time, so that way we can get a good amount of marbles hit the back wall, we'll get something like this. There'll be two maxima on it. The top maximum associates to hole A, and the bottom to hole B. And it's a little broad because the source was unpredictable, so the marbles can kind of come out at like a slight angle. They don't have to be perfectly through. But more of them are hitting around perfectly through, which is why we get those 2 sharp peaks. So this is what we get for marbles. Let's start closing some of the holes. So let's cover hole B first. What happens when we cover hole B? So what we'll get is what we call Na. So this is when the marbles can only get through A. And it's a sharp peak, or it's a relatively sharp peak. It's spread out a little bit because, again, the marble can come out at slight angles. If we do it with B, we get something very similar. So if we cover hole A and we only let them through B, we'll get something very similar except it's shifted down. So it's the exact same reflection. It's symmetric. And now if we open both holes. So what happens if we open both of them? We already know what happens, right? We get NAB. So this is what we said beforehand. If you look closely, you can actually notice that NAB is actually the sum of NA and NB. And this makes sense because the amount that goes through both of them should be the amount that goes through one of them and the amount that goes through the other. If we add them together, we should get the total amount. So this is our main takeaway from marbles. The amount that goes through A plus the amount that goes through B equals the total amount. Now let's talk about some waves. So what do we expect when we launch some waves in here? So first of all the waves will spread out. So waves can spread out over space. They don't come in lumps like marbles do. We have a marble and it's only located here. But a wave will spread out. That's why if someone stands to the right of me and to the left of me, then they both can hear me because the sound waves spread out over space. That will happen here. Now, the second thing that we want to keep in mind is that all the waves are the same size. There's two things I mean by the same size. One is that all the heights of the waves, so this is water waves, all the heights of the water waves are the same, so all the amplitudes are the same. And then it's also very periodic. So if we're getting hit by the wave, very rhythmic, has the same tempo. So those are our two conditions on these waves. And then the third thing we need to know is that the height of the wave at any given location is equal to the height of the wave from A plus the height of the wave from B. So the amplitude at any point is equal to the height from A plus the height from B. And we'll talk more about that in a moment. And what we're going to do here is we're going to make it a little bit different than the last one. The last one we had Play-Doh. The way we measured the amount of impacts from marbles is we said it was Play-Doh and we just counted the amount of collisions or the indentation. For this one, we're going to put some corks on a wire and attach them to the back wall. So the wire allows the corks to move up and down, but not side to side. And cork will float on water, which is why we're going to use it. So if a wave passes over where the cork is, the cork will move up and down. And what we're going to measure is the intensity of this up and down motion. That's what we'll measure with the waves. We're measuring intensity. And then we'll have a similar naming scheme where we'll have I for intensity. A will be the intensity from hole A, B from hole B, and AB from both of them open. Now, we can ask, what do we get? We run this experiment. We don't know what will happen. What do we get? We get something like this. Much different than the marble. The reason why we get this is because waves have something called interference. Now, what is actually interference? Okay, so why does this happen? So let's take a look at some interference, some wave behavior. So what we're going to do is we're going to cover each hole. We're going to do some experimentation again. So we're going to cover hole B and see what happens. So waves will come out of hole A, and they're going to spread out over space. Now, what exactly does a wave look like? So the maximum of each of these waves is going to be corresponding to one of those lines on the previous slide. So the maximum are located by the lines on the circle. And this is going to be how we picture the wave. So the waves just move very uniformly, same speed, to the right. This is what we're going to be picturing for each wave. So that's what we picture here. Those maximum, those top spots are these lines here. And they're just going to be spreading out. Actually, I should use this hand. They're going to be spreading out this way. Okay, and then if we cover the other hole, so we cover hole A, this is what we get. Same thing with B, it's very symmetric. So now what happens if we open both holes? So the interesting thing about waves is that they can actually pass over each other. They can pass through each other. Two marbles will always bounce off each other, especially if they're indestructible, like we're saying they are. But two waves can always pass over each other. They can always pass through each other. What happens when they pass through each other? That's what we're going to be talking about here. So this just illustrates that two waves can pass through each other. This is the red and the blue just happily going through each other. Well, what happens to the actual water? If this is water, what actually happens? So what actually happens when they pass through each other? This goes back to what I said before, that the height of the wave is actually the sum of the two waves that pass through each other at that spot. That's just a fancy way of saying that they add. So when two waves pass through each other, the net result will be the green. So notice that at some spots, the green surpasses both of them. At some spots, it's just completely flat. Those are going to be the spots that we're really interested in right now. So the first one that we're going to talk about is constructive interference, where, and I know it's very hard to see right here, so let's make the red a little dashed so that we can see behind it. When the red and blue pass over each other, they double in height. So now the amplitude of the water, if this was water, is going to be twice the height than what it was if only one passed over. In the other special case scenario is what happens when they're completely out of sync. The top of one meets the bottom of the other. They just completely cancel out. And this is really interesting. We could send two waves in and then just get completely flat water. So these are going to be our two special cases. So now back to the two-slit experiment. So let's keep in mind that the amplitudes add. I didn't change that one. Let's picture it lowercase a. So let's just draw a vertical line down, and let's look at what happens. Imagine if you put the back wall there. So at each of these little dots is a crossing between a blue and a red line. That means that's going to be a maximum meeting a maximum. That's going to be a wave twice as high. So all these are going to be maximum spots. But notice, we got maximums, but we also got space between them. And in the in-between, we get some destructive interference. So they cancel. So what we end up getting is a series of maximum separated by minimum. This is what we get. So the intensity, if we have both of them open, ends up resulting like this. And the reason why there's a dotted line here is to just show this is the center. And if we look through the center, we notice that there's always going to be a crossing line. Two crossing lines there. There's always going to be a maximum in the center. And you might ask, well, why does it decrease on the sides? This is because the intensity is directly related to the energy that the wave carries. And as the wave spreads out, it carries less energy. So there's less distance the waves have to travel at the center compared to the sides. So it has to just travel farther to get there. So it just loses some energy. And that's why we get a maximum in the middle and maximum on the sides that decrease. So what we're going to do again is cover each hole at once and look at the intensity of the quark motion. So we're going to cover hole B, and we already said this before, but this is what the intensity is going to look like. It's going to be a maximum again, and it's going to spread out, and it's going to decrease because the wave just carries less energy towards the ends. Now we do the same thing with hole A. We cover hole A, and we get something similar. It just spreads out because the wave loses energy. But with both holes open, again, we get this. And what do we take away from this? Well, the intensity, when both of them are open, is not equal to the intensity from A and the intensity from B. And the reason for this is there's interference. If there's no interference, this would equal. So what's interesting is actually the intensity is related to the energy, and it's actually just the square of the height of the wave at that point. So if we square what the height of the wave is, we get how much energy it carries. And for the mathematically minded people, if we square two sums, then we get a squared plus b squared plus something else. And that something else is going to be the interference term. A lot of information there. Now we're going to be talking about electrons. So electrons will come one at a time, just like marbles. We will be measuring the amount of electrons that hit the back wall, just like the marbles. And that's basically all we need to know. So it's very similar to the marbles. We can't predict whether it's going to go through A or B. Not a very good launcher. They come in lumps, like marbles, one at a time, like marbles. And all the same size, like marbles. So what do we expect? Do we expect the green or the purple for electrons? Everything's been the same as marbles, so purple, right? So when we run the experiment, we get the green. Lo and behold, we don't get purple. We get green. Why do we get green? This is weird. In school, we learn to look at electrons like little tiny moons that orbit the atom like a planet in a moon system. So you'd expect that it to act like a marble, right? It doesn't for some reason. This is really weird. This is the first weird thing. We get some sort of interference. So we ask, what does the electron interfere with? There's only one at a time. It can't interfere with anything. Does it interfere with itself? And then you might be like, oh, I know what it is. The electron doesn't just go through hole A and then hit the back wall, or B and hit the back wall. It takes some funny pattern. It goes out A, back in B, makes a loop, it goes back out B, does all this weird stuff. So we make a prediction that maybe the electron makes motion like this, and then it hits the back wall. And we can't predict exactly what's happening because it's unpredictable motion. So what's happening here? But we can test this. The first way we're going to test this is we're going to cover each hole again. So first, we're going to cover B, and we're going to see what we get. What we get is we get what we would expect in this case. The amount that went through hole A is just going to be spread out just like it was for marbles. And then we cover B, and we cover A, and we get what we expect. Nothing strange here. But when we open both of them, we would expect that the total amount to reach the back wall is going to be equal to the amount that went through A and the amount that went through B. So we expect this. And we would really expect this. So let's make it purple. So this is what we would expect. But this isn't what happens. We get the green. And NAB purple is not equal to NAB green. So why? When we add up the contribution from one and then the other, we get purple, but then when they're both open, we get green. Then you might pick, oh, I got a good idea. Let's leave them both open. Let's not close one. Because maybe that messed up something. Maybe only going through one is just disrupting it for some reason. So let's leave them both open. And we're really going to get nature on this one. We're going to confuse her. We're going to just look to see which hole it goes through. So they're both going to be open. We're just going to try and figure out which hole it goes through. So we're going to be watching. We'll just set up a little tiny detector behind each of them. And we're going to watch. So what we do is we set up some detectors, which are labeled by the smiley faces. And we set up a table. So we just mark off. So one electron shoots through, goes through A, we mark yep, and it doesn't go through B. The next one comes around, went through A again, mark yep. So what happens when we do this experiment? So we'll make a big table, we'll do it a lot of times. And lo and behold, we get purple. That's not what we wanted. We wanted green. What happened? We didn't close any holes. We left them both open. We should get green. We don't. We get purple now. Nature is very finicky. We thought we had her. She had us. So what's happening here? So let's talk about exactly what happens when we measure. These little smiley faces just represent some photons. We're going to try and figure out if the electron went through A or B. We just need to shine some light. Look through A or B. And when the electron does something with the photon, then we know it went through A or B. And then it hits the back wall. So you might say, let's talk about what we can take away from that experiment. What we can take away is that when we look and we know which hole it goes through, we get the purple. And when we don't look, we get the green. So when we know, we get purple, don't know, green. So this is something we might say when we don't look. Even if we're not looking, if the only way to get from the source to the wall is through A or B, then there's nothing, like, how could the electron do anything different? So the electron must be going through A or B. Can't go through both. Doesn't, like a marble can't go through both. Why could an electron? But what's funny is actually that's false. And we'll talk about why it's false a little bit later. But the funny thing is, it's not just false, it's very false. It's very wrong. We cannot say that the electron went through A or B without looking. We just can't. We don't know. We didn't look. We can't prove it. So if we look on the right-hand side, it's just summarized. We got look in purple and don't look in green. Just so that way we can keep track of what we'll get if we do one of them. Maybe the light is just too strong. Maybe just for some reason, the strength of the light is just interfering with the electron, causing it to shift from green to purple to green to whatever we're interested in. So let's trick nature again. I got an idea. Last time it didn't work, but I got an idea. Let's turn down the intensity of the light. Let's turn it down. If we turn it down, then surely it won't disrupt the electron too much. Let's turn it down a little bit. You can tell we turn it down because the smiley faces aren't as yellow. So there's one problem with this. Light also acts like a particle. Photons are the particle of light. So when we actually turn down the light, we're not turning down anything but the amount of photons that are passing through. So we're just decreasing the amount of photons we're using. If we decrease the amount of photons we're using, we expect not to get every electron that goes through. Right? We're going to be missing some if we're not using as much light. So what we're going to do is we're going to make that table again. And when we detect an electron through A or B, then we're going to use the one that hit the wall. But if we don't detect one, we get rid of it. If it hits the back wall, but we didn't see which one it went through, then we just get rid of that data point. So what do we get when we do this? Oops, a little ahead. So what happens? So what happens is when we find out if it went through A or B, we get the purple still. And when we actually missed it, we get the green again. So we get the same thing. Turning down the light doesn't do anything. So that's where this question comes in. What does this mean for the state of science today? That's a great question. Myself? So the first thing that we take away from this is we can't have 100% certainty on our measurements. We have a little bit of uncertainty. And this can be, so last time I did this is our second time going through this presentation. Rob was nice to point out that I didn't talk about the Heisenberg uncertainty principle, and this relates directly to the Heisenberg uncertainty principle. The second thing is we cannot predict what's going to happen. When we look at the green, when we don't look, we can't tell where the electron is going to hit. We just don't know what's going to happen. We can't predict if it's going to go through A or B. We can't predict what's happening with 100% certainty all the time. Third is that particles like electrons and waves like photons act weird. But the good news is they act weird in the same way. So that's at least something. And then this is actually what we call particle wave duality, which is another thing Rob pointed out that I didn't mention last time. We also get something called superpositions, which I didn't mention, and I won't mention until the next time. Yeah, little cliffhanger. The basic idea is that it goes to the statement that was false, that it went through A or B. It's kind of like an A or B now. We don't really know. Kind of went through both and neither at the same time. And then the last thing is probabilities. So if we look at the purple really quick and we think back to the marbles, if there's a sharp peak at a certain spot, it's a higher probability that the marble is going to land there because more just land there. So of course there's going to be a higher probability. Well, not of course, but we can reasonably guess that there's going to be a higher probability. So if we're talking about numbers, a higher peak for numbers relates to probability. And in the marble case, the probability that it went through A plus the probability it went through B equaled the total probability, that purple one. But that doesn't happen with the electrons. The probability that it went through A was that blue line. The probability it went through B was that red line. And when we add those, we don't get the probability that it went through A or B when they're both open. We don't get green. So probabilities don't add the same anymore. That's really weird, but that's technical. We don't have to worry about that. This is weird. It's a weird experiment. We try to get nature, and nature got us. We're confused. We don't know what's happening. We can't know what's happening because we can't look at the electron, because if we look at the electron does weird things. So where are we? What really happens in this experiment? And that's where we're today in science. We don't really know. So this leads to different interpretations of what's actually happening here. We don't know if it's going through A. We honestly don't know. And we don't know why looking changes it. So the first one we'll be talking about, the first reason why this happens, is going to be Rob's favorite interpretation, called the many worlds interpretation. Thumbs up. The second one we'll be talking about is probably my favorite, which is relational quantum mechanics. And then I don't know which ones we'll be talking about after that, so I just listed a couple. So there's one called cubism, there's one called spontaneous wave function collapse, which is actually the one you typically learn when you first study quantum mechanics in school. But most people in the field don't think that's the way to look at it. And there's many, many more. I think I have to fact check this. The last time I heard, there's about 150 different interpretations. And that's just the ones that are listed on Wikipedia. So, first of all, if there's so many, why does it matter? The reason why it matters is different interpretations can lead to different questions. If you look at it from the many worlds view, you might ask a different question than if you did from the relational view. The important thing is that we can't tell the difference between any of the interpretations. All of them, there's one exception to this. They are just used to explain what we know. They don't predict anything. So it's not a theory, it's an interpretation. Can't tell the difference. And there's one that's called, I think, the David Bohmian interpretation or something like that, that predicts one thing different or something like that. But we do not have the technology or near the technology level required to actually perform the experiment, so we don't know. And maybe in the future, when we have the technology, we'll be able to either rule out one out of the 150, and we'll only have 149 now, or we can prove that one right, and then we can drop 149 up. Either way, this is where we're at right now. When we look at the electrons, we get something different. When we don't, we get something different. There's many ways to explain what's happening. Can't tell the difference between any of the explanations. And that's it. Screen sharing, and we're back to just me and you. So that's what's happening. Quantum is a whole lot of weird.
It is.
Yeah. Did I leave anything out this time?
So when you were talking about the Heisenberg uncertainty principle, why it's important with regards to this experiment is that when we're having the electrons go through one or two, A or B, and when we have the detectors there, the Heisenberg uncertainty principle says that you can't know a particle's position and its velocity at the same time. And when you have something that's trying to detect the electron, you influence its position or its velocity. So it changes the state of that particle when you try and detect it. So that's why it's important in relation to this experiment.
Okay. Anything else I left out?
No, I think you covered everything else.
Okay. Good.
This
Okay.
one you did good.
And so I'm going to take it upon myself. So let me explain why I was the one who went through this mostly today. The reason why is because I focused on quantum when I got my degree. That was my focus. And Rob focused on the bigger things. So he's going to be explaining the bigger things when we come to it. But I'm going to take it upon myself to try and do what Feynman said, which is to explain all the other weird things that happen in quantum mechanics with the two-slit experiment. So later on in this series, when we talk about entanglement, which I still think we have to finagle this experiment to get to entanglement, but we can. It's just not as direct as it was before. So I'm going to try and explain entanglement with this, Schrodinger's cat with this. I'm going to try and explain the relational quantum mechanics with this. And if there's anything else that you, the viewers, find weird about quantum mechanics and you want to hear an explanation that is related back to this, please leave a comment down below. Any final comments, Rob?
No, I'm excited to see what begets of this whole series. I'm very excited to see it in its entirety.
Oh yeah,
Since
me too.
the beginning, we have planted the seeds, if you will.
Oh yes. That's me planting seeds. As you can tell, I'm a theoretic. I do theory, so I don't actually do anything with my hands, which means I don't garden, which means I look like an idiot when I garden.
Yeah.
Okay, let's just end it now. Have a nice rest of your day, everyone, if you made it this far. Please, if you made it this far, down below, this is just for me, down below, rate my explanation of this on a scale of 1 to 10. Okay, so 1 being not that great, 1 being like a really bad college professor, and then 10 being like who's a really good explainer that people will know? Veritasium.
Bill Nye or
Bill Nye. Yeah, Neil deGrasse Tyson. So on one end, one is a bad college professor. On the other end is like Bill Nye, Neil deGrasse Tyson, one of them. So just scale me between there. And if you don't give me a 10, which I'd be surprised if you do give me a 10, give me one piece of advice that I could do to get better for next time. Now, with that said, have a great afternoon, day, evening, night, whenever you're watching this, if you made it this far. And stay nerdy.
stay nerdy.
Blah, 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 blah. Okay, okay, yeah, okay. So, again, okay, 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 okay. Okay, okay, okay. Okay, 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 okay. Okay. Yeah. Ah. Um. uh. Okay. 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 Um. The okay. 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 But okay, let's just end it now. Okay? Okay. And stay nerdy.
Stay nerdy.
Yeah.